So how's the preparation going? How are you doing with linear algebra? Better? Let's just wait a couple more minutes for others to join, and then we'll just continue as per usual. Well, okay, I think we can start. So the topics for today are eigenvalues, eigenvectors, diagonalization, inner product and length, orthogonality, Gram-Schmidt process, symmetric matrices, and I also might throw in some LU decomposition if we manage. But if we don't, I will just provide you some links to YouTube videos that explain this very well. And also, I've seen somebody asking for answers and solutions for the exam questions. I don't have them, unfortunately, but I tried to solve some of the last questions, like fourth and third questions, and I think I can explain them to you if we have time. So what we can do is we can have like 5 minutes breaks between those topics and not 10-minute breaks like in the middle. 5 to 3 minute breaks just to kind of refresh in our minds, and we will just work through those step by step. Yeah, so let's see. What do we have next? An eigenvector of an n by n matrix A is a non-zero vector x such that it satisfies this equation for some scalar lambda. A scalar lambda is called an eigenvalue of A if there's a non-trivial solution x of this equation. Such an x is called an eigenvector corresponding to lambda. So what does that mean? It means that for like a square matrix, we might have a set of vectors that satisfy this equation for some value, and this value is called an eigenvalue. So eigenvector, eigenvalue, they correspond to each other. And geometrically, what does that mean? What does this equation mean? It basically means that for this specific vector, this matrix as a transformation, what does it do? It just stretches this x vector, which is an eigenvector, by a certain value, lambda. So this is basically stretching, or maybe a flipping if the lambda is negative. So geometric meaning is quite simple. of this idea. I think it's pretty clear. So let's see. Let's see what's next. I maybe made some notes regarding this. Yeah, so this matrix transforms the vector to a multiple of itself. I just explained that. And how to check if a given vector is an eigenvector. Basically, you just multiply a matrix by this vector and see if the resulting vector is just a multiple of the initial vector. Let's see an example. So we are given matrix A and V and asked to check whether V is an eigenvector of A. This means that we just multiply A by V. Yeah, so this step is 6 minus 30 minus 24. Yeah, and 20, something like that. And then we just compare it to the initial V. And as you can see, if you multiply V by minus 4, you get exactly that. So the only most important part here is this quality. AX equals lambda X, or some lambda or X, and those lambda is an eigenvalue corresponding to X that is an eigenvector. And this is how we can check this. There are also multiple ways to calculate eigenvectors and eigenvalues. We will see a couple of them. Yes, so V is an eigenvector of A corresponding to the eigenvalue minus 4. So here, lambda is equal to minus 4. So this should be fairly clear. Yeah, sounds good. If we have any questions, you can just ask them. If not, I'll just continue. Since we are kind of in a rush today, you can, if the question is urgent, you can use your microphones. But I'll be checking the chat. Okay. How to check if a given scalar is an eigenvalue of A? This means that if we could rewrite this equation in a different way. Yeah. Give me a sec. Yes, so let's see. We are also given this matrix A, and we will need to check whether lambda what we might do is we would say that lambda is an eigenvalue of A if there is a non-trivial solution to this equation, or we could just rewrite as A minus 7 multiplied by the identity matrix applied to X equals 0 vector. And those two things are vectors. If this matrix has a non-trivial solution, meaning it has multiple, so infinitely many solutions, because if this matrix has a determinant that is non-zero, this equation would just have one solution, a trivial solution, just a set of zeros. But if this matrix has a non-trivial solution, that means that 7 is an eigenvalue of A. Yeah, so same as that, just this equation. And what we do next, we just solve this matrix. We see that those rows are linearly dependent, meaning that this in fact reduces to this simple matrix. And therefore, 7 is an eigenvalue of A. So there's a free variable, so non-trivial solution, 7 is an eigenvalue. This is how we check whether a certain value is an eigenvalue of A. We just solve this system and see if it has free variables or not. And a small note, the matrix has X that as a solution. Any vector of this form is an eigenvector corresponding to 7. So to eigenvalue equals to 7. Yeah, so you can check, and basically we could just multiply this matrix. Let's take x2 equals to 1, 1, 6, 5, 2. Let's multiply this by 1, 1. And what we will have? 1 plus 6 equals 7. 5 plus 2 equals 7. And we can see that this is exactly 7 multiplied by 1, 1. Or lambda x. Yeah. This is ax. So ax equals lambda x. This is exactly what we need. So this is just a recap of what we learned, how to check if a given scalar is an eigenvalue of A. Given the scalar and the matrix, we just solve this for X. If there's a free variable, then lambda is an eigenvalue. X is an eigenvector corresponding to this. So X is some kind of solution, yeah, of this system. And another notion, eigenspace of A corresponding to lambda. Eigenspace consists of 0 vector and all eigenvectors corresponding to lambda. So why is it called an eigenspace? Meaning that is a space in and itself, and it's supposed to contain 0 vector because all spaces are supposed to contain 0 vectors. And also, if you add two eigenvectors, their sum would also be an eigenvector. I think it's quite logical. Yeah, so if you let's say x and y are both eigenvectors, vectors. If you just ax plus y, this would be ax plus ay, and this would be lambda x plus lambda y, and then you just take out lambda. So yeah, so their sum is also an eigenvector. And also if you check multiplication by a scalar, so k is some kind of r, non-zero. Well, 0 could also do because we have a 0 vector. You could just, k is eigenvector, just here, this here. Akx is just kax is just k lambda x or lambda kx. So yeah, this is the original vector. So that's why eigenspace is a space. Let me check for questions. I think we have no questions. Good. All eigenvectors are solution to this equation, yeah, corresponding to lambda. We might have multiple solutions in a sense that in parametric form, we might have something like this. So xi multiplied by something plus xj multiplied by something, by some vector. Yeah, so, and these two vectors, just an example, would be our eigenvectors. Yeah. This is also a basis for eigenvectors. I'm just getting ahead a bit. Yeah, so eigenspace is the same thing as the null space of this matrix. Just as I said, it's the same thing as a null space of our matrix. Do we remember what a null space is? I think we do. Yeah, so it's just what transforms into 0. That's so the solution, everything that is this, so E null A is any x that satisfies this equation. Yeah. no, pardon, no. Yeah, this is what I need. Yeah, so let's look at this question. This is an exam question. And we're asked to find a basis for eigenspace corresponding to eigenvalue lambda equals 3. So what do? We need to solve this kind of look, what does this give us, and then solve it. I think, do you guys want to solve it yourselves? Parametric columns of a minus 3i. Let me get back to that slide. Yeah, so we just need to solve this and see what x give us, and then the parameters, kind of the vectors in front of the parameters, for example. Yeah, so x2 and something would be the basis for our eigenspace. I think it's better if I show you the solution. If you just look at the solution, it's same as finding a basis for the null space of matrix this. Yeah, so a minus 3i. It's not the same thing as column space. Don't make that mistake. Null space and column space are very different things. So we just found the a minus 3i. This is this. And 4 minus 3 equals 1. 1 minus 3 equals minus 2. Same here, and all the rest values stay the same. So this should be fairly easy. And then we solve this matrix. So yeah, you could just get rid of those, because this row and this row are basically the linear multiples of each other. So we could just get rid of this one and scale this by, let's say, by minus 2, and then subtract the first row from here. And that's how we get to this matrix. And from here, we can say that x1, yeah, so this is our free variable, x1 equals minus x3, x2 equals x3, and x3 equals x3. So x then is x3 minus 1, 1, 1. Yeah, so exactly that. If I'm going too fast, you can just don't hesitate, because I want to cover a lot of things. How do I know when the variable is free? Could not learn that. Okay. How do you know if the variable is free? So let me show you. Do you remember the idea about pivot positions, pivot columns? So each column here, for example, we have 3 variables. Each column corresponds to a variable. So x1, x2, x3. Yeah. And the variable is considered free if it corresponds to a column that doesn't contain pivot positions. Okay, so this column doesn't contain pivot positions. If it had like 1 here and 0, 0 here, then it would be a pivot column and we would not have any free variables. But in this case, we don't have pivot positions here. Our pivot positions in this matrix are these ones. So 1 in the first row and 1 in the second row. And therefore, x2 and x1 and x2 are not free variables, and x3 is a free variable. This is the topic of the first lesson, and I think you should go over the first slides if you're not clear on that. And when to stop reducing. So you stop reducing whenever you get to this shape. Yeah, so this shape, this is how you get an echelon form. Yeah, so you stop reducing here, like you have a matrix with kind of steps, and like each vertical length of step is 1. If you get something like this, yeah, 2 steps, that's not correct. And then this is the echelon form. This is reduced echelon form. So how does reduced echelon form and just simple echelon form differ from each other? Reduced echelon form has 1s as its leading values. So here's supposed to be 1, and here's also supposed to be 1, and also above the pivot position, we have 0s. Okay, so don't worry. Just, so is it always once in diagonal and the rest is 0? Not always. Not always. So let me give you an example. So this is the case that you are referring to. Yeah, this is also a reduced row echelon form, but we could have something like this. Yeah, so 0, 5, 0, 0, 0, 0. As you might have noticed, this is by definition. So our leading ones are to the right of the rows above it, and everything below is 0. Everything above the leading position is 0. So yeah, just go over the definition of a ref. So here on this diagonal, we don't have a 1 here because this column, I think of ours right though. In this case, yes. It's always like that. Well, in this case, we don't have a 1 on diagonal. Yes, the identity matrix, it's true. So I is always, I mean I'm sorry, yes. I thought, yes, this is I. Yeah. And yeah, sorry. Sorry, I didn't understand the questions. Yeah, so this is ref. This is just ref, an example of refs. Sorry guys, I didn't get enough sleep, so I kind of might misinterpret your questions. Bear with me. Yeah, so why is this called an identity matrix? Because in algebra of matrices, this is something above linear algebra. It behaves like a 1. If you multiply something by an identity matrix, it doesn't change anything. So if you multiply a number by 1, it also doesn't change anything. So that's why it's called 1. And you can just test this property. You can multiply any matrix by I, and you'll just see that, yes, it is true that, let's say, A. So, yeah. So I basically behaves like 1 in matrices, like 1 behaves in numbers. Okay, where was I? Yeah, so I just explained how we get a reduced row echelon form. How do we consider how do we know which variables are free or not? The ones that correspond to a non-pivot column, there are the free variables. Yeah, so this part should be clear. That's how we got our vector x3, which would be the basis for the null space of A minus 3I. Yeah. So this should be also quite clear. Let's go over this again. We found A minus 3I, we solved it, we found the solution for this matrix, and this is the basis. Basis for null space A minus 3I, and also a eigenvalue corresponding to lambda. Yeah, so eigenvector vector corresponding to lambda equals 3. Sorry for the writing, I am trying. So how to find all eigenvalues for a matrix? Actually, we could just say, so we could just say that if the determinant of the matrix is 0, this also means that this has infinitely many solutions, which is exactly what we need. So if we just we want to solve this and find non-trivial solutions. And what we also can do is to say that this matrix is not invertible, meaning that its determinant is equal to 0. And in fact, if we just consider lambda as a variable, sort of, yeah, so like x, this would give us a polynomial. Yeah, so if we remember how to calculate the determinants. So for example, let's say we have a matrix A, 1, 3, 4, 0. I think it will be more clear when we do an example. Let's calculate A minus lambda I. We just take lambda as a variable. I mean, variable in quotes, because it's not the variable of the system of linear equations. It's the variable in the polynomial that A minus lambda I equals 0. And so we have this as our matrix, and we want to find its determinant. And so 1 minus lambda multiplied by minus lambda minus 3 multiplied by 4. So cross multiply and then subtract. And that should be equal to 0. Let's just rewrite this polynomial of the second degree. And you could see that the roots of this polynomial is 4 and minus 3. And 4 and minus 3. So these two values are the eigenvalues of matrix A. Yeah, we could check that, but let's do this check as a homework. Yeah, if you have any questions about this part, you can just ask them in the group chat. Let me check. Are we always minusing? Do you have an example of eigenspace? Okay. Are we always minusing? So let's say we have just a small, let's say we have a vector A, B, C, D. Yeah. And the determinant of A is AD minus BC. Okay. This is just the definition. Okay. I think you should kind of go over the second slide as well, just to kind of figure out what determinants are. This is just specific to case of 2 by 2 matrices, okay? And if you're referring to this minus, well, that's just how we define lambda, okay? We're minusing here. Do I have an example of eigenspace? I think if I go back to the previous, wow, why did I make so many slides? Yeah, so this, in fact, so eigenspace is the 0 vector corresponding to this lambda. And this vector, multiples of this vector. which is basically a lambda. Corresponding to lambda equals 3. Why is this an eigenspace? Because if you take x3 multiplied by this vector and you multiply it by a, so if you take like something like ax3 multiplied by minus 1, 1, 1, it would just end up being this vector. Minus 1, 1, 1, okay? So this is the definition of this kind of the eigenspace. Considering the definition. There could be two basis vectors in the eigenspace if the multiplicity of our lambda is 2. I will talk about multiplicity in a minute. So we were here, then this, and then that, and then that, and then this. Are we following? I might be going over stuff a bit quicker than I did in the previous lectures. Okay, good. So eigenspace is not just one vector, but multiples of it. Or if we have two vectors, like in a basis, it's just the linear combinations of those two vectors that form an eigenspace. Okay? Just don't worry, we will go over this. It's coming. So that's how we find eigenvalues for a matrix. We just solve this polynomial. Yeah, so you need to find this matrix first, a minus lambda I. Keep lambda as lambda, yeah? And then you find the determinant of this matrix. And then you kind of equate this polynomial to 0, and you solve it as a polynomial equation. So this determinant of a minus lambda I equals 0 is called a characteristic equation. Just remember this term, characteristic equation. And this, just without 0, is called characteristic polynomial. Okay? Just remember that. Yeah. This thing. So the eigenvalues of triangle matrix are entries on its main diagonal. I think this should be fairly clear for someone who remembers how I kind of how I showed you what the determinant of a diagonal matrix is. Because if we take a diagonal matrix, yeah, and if we subtract, let's say A is diagonal, and we subtract another diagonal matrix, which is lambda I, we would still get a diagonal matrix. Yeah, so this is still a diagonal matrix, meaning that its determinant is still the product of everything that is on a diagonal. So a minus lambda I would have a shape, let's say this, yeah, would have the shape of minus lambda, a 2 minus lambda, a 3 minus lambda, a 4 minus lambda. Here we have zeros, and here we have something that didn't change, the same thing that's here, so upper triangle matrix. And the determinant of a minus lambda I would be just a 1 minus lambda, a 2 minus lambda, a 3 minus lambda, a 4 minus lambda. And here you might think like, wow, I could just use Gauss-Jordan elimination and turn any matrix in a diagonal one and then just, find easily all the eigenvalues, but no. Yeah, so let's first do this. Let me show you this example. So for this specific matrix, which happens to be lower diagonal matrix, eigenvalues are 1, -2, 3, and 4. But however, if you perform the row operations, so meaning if you try the Gauss-Jordan elimination algorithm, this changes the eigenvalues. So you can't do that. You cannot turn a matrix in a diagonal one and then just consider that the eigenvalues stayed the same. No. Okay, so just remember this. Just remember this is very important. Okay. So the only way to find all the eigenvalues is to solve the characteristic equation. Yeah, so another notion, multiplicity is the number of times an eigenvalue occurs in the characteristic polynomial. So here, the value 5 occurs twice. So lambda equals 5 has a multiplicity of 2. Lambda minus 3, so lambda equals 3. It occurs once, so it has a multiplicity of 1. And lambda equals 1 has a multiplicity of 1. Yeah, so if you have any questions, I can give you a moment. Okay. Yeah, so we're done with eigenvectors and eigenvalues. What you guys can do is take like a 4-minute break. Maybe I can give you a simple equation. Try to find eigenvalues of this. Yeah, so all eigenvalues, okay? Just try to do this. 4-minute break. I'll just have some matcha. I need caffeine in my system. So I think nope, you can't. Can I reduce the matrix to a triangle and find the determinant? No. You can't, because sweeping some matrix in A in a triangle matrix changes the eigenvalues. Remember that. You can't do the Gauss-Jordan elimination. You can just turn it into a triangle and declare that the values on the diagonal are your eigenvalues. You just have to use the characteristic equation. So to solve this, that a minus lambda I equals 0. So the roots are eigenvalues. Okay. Yeah. Just remember this. I kind of so regarding this question, so the a minus lambda I would be 1 minus lambda 2, 3, 4 minus lambda. So the determinant of this thing, a minus lambda I, is 1 minus lambda by 4 minus lambda minus 6, and it should be equal to 0. And this gives us quite an unpleasant equation. Unpleasant in a sense that we have square roots. I'm sorry, this is lambda, not x. Yeah. And lambda 1 equals to 5 minus square root of 33 divided by 2. And lambda 2 equals to 5 plus square root of 33 divided by 2. I just came up with this on a whim, so that's why we have roots here. If I just thought about it a bit more, I might have came up with something that has a bit more nicer answer, but that's okay. And we can go on to the next topic if you don't have any. What do you solve that? I don't remember the from school. Okay. Okay, it's okay. So how do you solve this equation? Let me just remind you. A squared plus bx plus c equals 0. X. So do you remember discriminant? Yeah. So this is the discriminant. So x1 would be minus b, let's say minus square discriminant divided by 2a. X2 equals minus b plus discriminant divided by 2a. Okay. And this is, we can do that if discriminant is more than 0. If it's less than 0, we would have complex numbers in the answer. So the roots, so this equation wouldn't have roots in the R, it would have roots in the C, so in the complex numbers. And if the discriminant is equal to 0, this means that we have only one root. So minus b divided by 2a, okay? 4 times AC. Okay, so that's that. Yeah, math tends to just slip out of your memory if you don't use it. That's true. That happens to me all the time. I just like So this is true. And then why? Why is that true? And then I have to go on like trying to find my old notes and books and then check this and then that. And yeah. So math is just intuitive, but you tend to forget it. So it's okay. It's okay. Don't worry. We can just go on, I think, if no more questions. So let's see the diagonalization. We say that A is diagonalizable if there is an invertible matrix P and a diagonal matrix D. Okay, that A, P, D, P inverted. So A equals P, D, P inverted. Yeah. So there's a certain basis in which our matrix could have a diagonal form. Yes, so this is what means. Not all matrices are diagonalizable, unfortunately. Otherwise, our life would be very easy, or maybe not. But yeah, sometimes we have a certain invertible matrix P that could just transform our matrix A into this diagonal matrix D that has non-zero values or maybe zero values on the diagonal and everything else is zero. Okay, so let's see. Yeah, so the PD diagonal matrix contains the eigenvalues of A. And columns of P are corresponding eigenvectors. We just need to write them in the right order. So for example, you have your matrix A. You found its eigenvalues. And you found its eigenvectors. And you can just transform your matrix A by using this formula in the diagonal form. In fact, you should use this formula for. So A is here. You multiply it by B inverted. Yeah, it's like sassy B. If I told you about this, no, P is here. Yeah, so like that. Okay, so yeah, and this theorem is true. So let me just read it out loud. An n by n matrix is diagonalizable if and only if there are n linearly independent eigenvectors of A. Okay, so we have n linearly independent eigenvectors of A. If there's less than that, if we don't have n linearly independent eigenvectors of A, that means that our matrix A is not diagonalizable. Too many syllables. Diagonalizable. Okay. Basically, there's no such basis in which our matrix A can transform into a diagonal matrix. Yes, so remember I talked about change of basis. I don't think I talked about change of basis for transformation matrices. Yeah, but that's not that hard. It's not a hard topic. You don't need to even know this. And how to see if A is diagonalizable? You just need to find its eigenvalues. Then you need to find eigenspace for each of the eigenvalues. And you need to find the eigenvectors corresponding to each eigenvalue and check if there are, in fact, n linearly independent eigenvectors altogether. Yeah, for each lambda, you just sum the number of those, and if you get n, then A is diagonalizable. So let's see. I believe I added an example. Yeah, so calculate the eigenvectors of A, calculate the corresponding eigenvectors, check if eigenvectors are linearly independent. If there are n linearly independent vectors, then A is diagonalizable. construct D by putting the that's how we construct D. Yeah, so we put the eigenvalues on the diagonal and fill the matrix with zeros. Eigenvalues with higher multiplicity occur multiple times, as many times as the multiplicity. So for example, we have lambda equals 2 with multiplicity of 1 and lambda equals 3 with multiplicity of 2. And then our matrix would be something like this. Yeah, so it occurs twice. Because multiplicity of, this is just an example, multiplicity of lambda equals 3, so of the value 3 is 2, so it should occur 2 times. Yeah, the characteristic equation is of that sort. Lambda minus 3 squared equals 0, okay? That was just a small note. Let me check the chat. There might be a question. No? Yeah, construct P by putting the eigenvalues corresponding to the eigenvectors in place according to matrix T. So first you put the vector corresponding to the first value, eigenvalue. Then you go on and then you put all of those corresponding eigenvectors. You have 2, yeah, corresponding to like this eigenvalue. It's better to see that on an example. And you just check that AP equals DP, so they're similar. Yeah, you could just check this. So let's look at this example. Let's first just write out this A minus lambda. Then we can write out the determinant. It's better in this case to kind of, you know, just expand along the row, not to use my pattern method, but to expand along the row, because this term occurs twice, and it's kind of hard to work with equations of the third order because you don't know the formulas. Actually, I knew the formulas how to solve this, but I forgot. So it's actually a very hard topic in math, how to solve equations, polynomial equations of order higher than 2. In fact, you can solve, you can have a general formula for those if the order is higher than 5, I believe, 5 and higher. So yeah, it just in this specific case, you could just expand along the row your determinant. Yeah, so you take this. We can do this if you want. Yeah, so let's do it. So for example, 1 minus lambda, the determinant. Yeah, so the determinant is equal to that. Multiplied by this minor, minus 5 minus lambda, minus 3, 1 minus lambda, plus 3, so minus, yeah, plus 3 multiplied by this minor, 1 minus lambda, 3, 1 minus lambda. Yes, this is a minor. And then we take this value plus 3 and multiplied by this minor. So you cross off this and that. You take 3 minus 5 minus lambda minus 3. Okay. And then you just cross multiply those, and you probably should get something like this. Something's wrong here. Yeah, it doesn't actually give me what I want. That's okay. That's okay. Yeah, so you might need to kind of know how to deal with those equations. You could also guess the roots, actually, kind of, because for polynomials, you could guess if the polynomial has a root that is, let's say, not even integer, has an integer root, it should be a multiple of 4. So as you can see, 1 and -2, they're both multiples, integer multiples of 4. So if there is a root, it should be a multiple of, if there is an integer root, it should be a multiple of 4. Yeah. So 1 and -2 goes as well. So, but actually, usually you just need to ask Wolfram alpha for the roots, and it will give you those roots. In solving polynomials, we have to do a square root and division stuff. So it's easy because we can do the calculator. Yeah. So for this polynomial, the problem is that it's of third order. So we have a lambda to the power of 3. The equation that the formulas that I showed you, they don't work for this one. They don't work for this one, and you're not allowed to use calculators. Well, I know, unfortunately, and I'm kind of worried about that, but I don't think there will be any trouble with that. For example, you just calculated this determinant. Just remember how we did that. We could just use the pattern method. Let's see, we just calculated that, and this is true. We could try to guess the roots. How? You might ask. Well, the way to guess it is to look at this 4 and consider all integers that divide 4. So we have plus -1, plus -2, plus -4. And if we can just take one of those and plug it in here, and if it gives you 0, this means that it's a root. So if we take, let's say, -1, we would have minus, let's say we are checking. Yeah, we are checking lambda equals -1, and this gives you -1 to the third power, -3 multiplied by -1 to the second power, plus 4. And this is not what we need, because this gives you 1 minus 3 plus 4. This is not 0. It's meaning that this is not a root. But if you take 1, for example, yeah, so lambda equals 1, and we're checking. This gives you -1 to the third power, -3 to the multiplied by 1 to the fourth to the second power, plus 4. And as you see, this is equal to 0. So yeah, you found one root. Good. You can actually stop here, because do you know polynomial division? This is not actually the part of this course. This is actually part of mathematics. And the problem with this is that in order to solve the third degree order equations, you need to know that stuff. I don't think they will give you those kinds of problems on the exam. They will probably give you some eigenvalues, something, and or maybe a 2 by 2 matrix that which has a characteristic polynomial of the second order. So you could use the formula that I showed you. So this shouldn't be too hard. But just in case you have trouble with that, you can use polynomial division. And let me see where I can write this. You can use polynomial division. And so yeah, so you have minus lambda to the third power minus 3 lambda squared plus 4. And since you know that 1 is the root, meaning that this polynomial has a multiple of lambda minus 1, and you can perform the polynomial division. And if you like multiply this minus lambda by minus lambda, squared, for example, you get minus lambda cubed minus lambda squared minus, I actually recently taught this to a, yeah, so this gives you minus, 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 something is, okay. Yeah, here's plus. Yep, so this is correct. Minus 4 lambda squared plus 4. And if you take now minus 4 lambda, you would have minus 4 lambda squared plus 4 lambda. Now you subtract this, you get minus 4 lambda plus 4. And if you multiply this by minus 4, yeah, you would get minus 4 lambda plus 4. This would give you 0. And this part would be basically your characteristic polynomial would expand into two multiples. Plus 4 equals lambda minus 1 minus lambda squared minus 4 lambda minus 4. You just take out this minus, yeah, and you would have minus lambda minus 1 lambda squared plus 4 lambda plus 4. And do you remember this thing? A plus b squared equals a squared plus 2ab plus b squared. This is also part of high school math, probably. And this, in fact, is lambda minus 1 lambda minus 2 plus 2 squared. Yes. This is not a part of linear algebra course, but I don't know if you've been taught this in school. And I don't think they will give you such hard questions. That's why I didn't dwell on this part. I didn't plan to dwell on this part too long. I am just doing this to show you how to do this. But just in case, let me just explain this to you. So let me go over this, what I did again. So first, I just wrote this, this matrix. I calculated the determinant by any way that you like, expanding along the row. Yeah, we did that last session. I don't know if you had a chance to go over it, so you might need to freshen this up a bit. But yeah, so then I got this polynomial by just combining the values, etc., etc. And then I am just trying to find the roots of this polynomial. And the potential candidates of the roots to this polynomial are the integer multiples of 4. So for example, 4 is divisible by plus minus 1, meaning that the product of the division would be the result of the division would be another integer, would be plus minus 1. Yes, would be another integer. So plus minus 1 is the candidate to the root of this equation, plus minus 2, plus minus 4. I chose minus 1 and minus 2. I checked. I've seen that minus 1 is not a root. I then checked 1. I've seen that it is a root. Then you could check plus minus plus 2 or minus 2, and then plus 4 or minus 4. And that's how you could have gotten the roots. But you could also stop here. So you found one root. And since you know that most polynomials, if all of their roots are real numbers, they kind of expand into the multiples of this form. So x1 to the certain power, like x minus x2 to the certain power, and something x minus xj to the certain power. Yeah, so any polynomial could be expanded like this. Yeah, if they have real roots. This is also math stuff. I don't know if you had this in high school. I'm not sure. But yeah, and you could do the polynomial division. I just did that. I hope you don't have to do this on the exam. But this is not the part of linear algebra course. This is part of just algebra in general. Maybe part of high school math, maybe part of some other course that you might have in the university. I don't know. I hope that you don't have to do this, because this is not necessary for a computer science student, in my opinion. Yeah, so we're here. Let me just go on to a fresher slide. Yes, so as we see, these are the roots. Lambda equals 1 is one root, lambda equals -2 is the second root, and this root has a multiplicity of 2. So it occurs twice in our polynomial. Yeah. So we are done with the first step, calculate the eigenvalues. And then we need to calculate the corresponding eigenvectors. In order to do that, we need to solve these two systems. They're fairly easy. This one is just obviously reduces to 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. This one might need some work. This is not a determinant, this is just a matrix. Yeah. This one might need some work, but it's also quite easy. If you just add the first row and the third row, you would get the second row. So you can just get rid of this row, scale those rows by 3 and kind of rearrange them. You would get like this thing, and then this thing. Yeah, so, and then this would just go on to 0, -1, 0, 1, 1, 0, 0, 0. Yes. And then you just solve those. Let me separate that. Is this part clear? Good, clear. Okay. Okay. Well, we have 3 more hours. There are a lot of topics to go on over. If we don't manage to get through that, yeah, so that's what I just did now. Yeah, and for lambda equals 1, we have one vector, and for lambda equals -2, we have 2 vectors. Yeah, so if you can see that those are the solutions to this equation. Yeah, so this is true. And then you need to check whether those 3 vectors, you have 3 vectors, whether those are linearly independent vectors. And if that's true, A is diagonalizable. So let's do that. I noted this in bold. All vectors are not multiples of each other. So 3 linearly independent vectors. You could also check this. For example, let's look at these 2 vectors. Yeah, so these two have this one has a 1 here and this one has a 0 here. So these 2 are not linearly dependent. And if you take this vector, it's also has a 1 here, but this has a 0 here, and this one has a 0 here, and this one has a -1 here. So they're pairwise linearly independent. And also we could check that this one is not in the span of these 2. So yeah, they're linearly independent. Let's just say that they are. And the next step, we would just construct the D. So we put the first eigenvalue here. Then we put the second eigenvalue here and here, because lambda equals -2 has a multiplicity of 2. So it occurs twice in our characteristic equation. Yeah. And then we just put our eigenvectors in P as columns in order. In the same way we put corresponding lambda, corresponding eigenvalues in our D matrix. So this is the V1, this is V2, this is V3, and this is lambda 1 and lambda 2 twice. Okay, this part is also clear. Oh, sorry, I paused share for a second. Yeah, okay. Good, good. If I'm going over this too fast, don't worry, just ask me. And we could check that AP equals DP. So you could just multiply this matrix by P, matrix multiplication, and then check if it's equal to this. Multiply D by P. Yeah, let's not do that. Matrix multiplication takes time, especially for 3 by 3 matrices. Imagine if you have to do a very large matrix multiplication. So yeah. So now that you have this, you actually can do a lot with your matrix A in a very simple way. It's very easy to calculate the powers of these matrices. So in order to do that, you just remember this formula, and then you kind of write out, yeah, so A multiplied by A, and then those two things just become an identity matrix because they're the inverse of each other. Yeah, so then D by D, since it's a diagonal matrix, and the square of a diagonal matrix is basically the square of a matrix with squares on its diagonal, yeah? So if you have something like A, B, A, let me just remind you. So then A squared would be A squared 0, 0, B squared. And so on for other powers. AN, A to the nth power, B to the nth power, okay? So this should be fairly easy too. It's just a lot of information. I'm worried if we are kind of getting this into our brains in time. So yeah, we just solved this one. This is the previous example. And this is the square of D. Just as I said, you just square the elements on the diagonal. And then we perform that multiplication. I think I did that. No, I didn't do it. Sorry. Do you guys want me to solve this to do the inverse of P? Where do we do the inverse? The inverse of P, we kind of assume, so we kind of, let me just get back to the slide. What's going on here? Why is it frozen? Oh no. Both theory. Yeah, so we kind of on this stage, we assume that we know how to calculate the inverse of matrices, and we just kind of calculate P inverse by knowing P. So if we assume on this stage that if we know P, and we know that P is invertible because the columns are linearly independent, and that's the same thing as saying that our matrix is invertible, we can just calculate the inverse of P by any methods that you like. I think I've showed you just one method with just sticking a I here and performing Gaussian elimination until you get this. Yeah. So let's not do the multiplication thing here. Yeah, so we're done with diagonalization. let's just have a small 5-minute break, because in order for our minds not to break, we just need to take breaks sometimes, just 5-minute breaks. Just since I've sent you the slides already, they're in the group chat, you can just go over them yourselves during the break and take note of that, what we have. So what are eigenvectors, what are eigenvalues, what are diagonalization. Okay, so don't worry. I think I need to take note that I'll try to find videos for you on how to solve polynomials on YouTube. So you would also be able to solve those, at least have some idea on how to do those. So yeah, I'll probably do that too. So I think we can get back. Now we have, this is not a large topic, it's just a little bit of theory. inner products and length. I think you all are here listening to me. Okay. Let's see. So orthogonality. No, inner products and length. Yeah. So let's say we are given two vectors, u and v. Then the inner product or dot product of two vectors is defined as such. So basically, we are just multiplying the first coordinates, and then we add to that the product of the second coordinates, and then etc., 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 until we get to the last coordinate. Just a small note that this is basically the same thing as multiplying the transpose of U by V, matrix multiplication. And let me give you an example. So let's say, let's do just a very simple one. 1 minus 2, 3, and V 1, 5, 4. Yeah, so let's just multiply them. U by V, you take 1 multiplied by 1 plus minus 2 multiplied by 5 plus 3 multiplied by 4. Yeah, you get 1 minus 10 plus 12. And in the end, what you get is 3. Yes, you get 3. Is this clear? This definition? Because it is important for the upcoming topics, and I need you to understand that. Okay? Are we clear on that? Okay, good. There's another definition of inner product. It was not in your course, so I kind of skipped it, but I can talk about it a bit later. And you could also define a vector, a length of a vector as such. This is called the norm of a vector. That's why there's another term called normalization. You just divide by a norm and you get a unit vector. Yes, so it's a square of of a dot product of a vector by itself. Yeah, so that's how we define vector. And let me just show you why it's true. So for example, let's take a 2 by 2 case and the standard coordinates. So let's say we have a vector u. Yeah. So its first coordinates is u1, u2. You can see that u2 here is the side of a right triangle. u1 and u2 are the sides of a right triangle. And if you want to calculate the length of u, which is a hypotenuse in this right triangle, you just need to add squares of the sides and then take the root of it. And in 3 by 3 case, this would be a diagonal of a parallelepiped. I don't know if you know this term. It's a part of stereometry. So you would have this, let's say this diagonal would be the length of your u vector. Yeah, and you would have basically Pythagoras theorem twice. Yeah, so once here somewhere. So this is u1, let's say this is u2, this is u3. And that's why it would give you square root of u1 squared plus u2 squared plus u3 squared. Parallelepiped. Yeah, I'm not sure how you're supposed to pronounce this in English. But the term is the same in most languages. Are we clear on this point?
You're muted.
Oh no, sorry. I don't think I pressed this. This is weird. Why? Yeah, I see why I'm muted. So yeah. How long was I muted? I think not too long. Yeah, so we can normalize a vector to create a unit vector by dividing the vector by its length. So for example, do you remember vectors? And so when we multiplied a vector by a scalar, it just stretched or shortened, but it preserved its direction if the scalar was positive. Yeah, in this case, norm is always positive because it's basically square root of sum of positive values, or maybe zero values, but it's still, it should be a positive number if this vector is not a zero vector. So you can divide by it, and you would preserve the direction of u. You would just have a new length that is equal to 1. Yeah, so this is u normalized. Yeah, and its length is 1. Yeah, unit vector. Okay. This should be also fairly clear, I hope. Do we have any questions on that? 1 minute. Oh, sorry. Yeah, but everything is on the slide, so you probably understand this. So let's say we want to normalize vector v. In order to calculate its length, you just square its entries, then add them up and take a square root of this. You get 9. Yeah, so 1 plus 4 plus 4 is 9. Square root of 9 is 3. And after that, you could just divide the entries of your u by 3. And this is the unit vector u. Sometimes it's denoted by e, sometimes it's denoted by u. So you divide each entry by 3, and this is your new normalized vector. It has a length of 1 and the same direction as the original vector v. You can check this for yourself. You could just square these 3 values, add them up, and you would just get 1. So that's okay. And we could use inner products to calculate inner products and lengths to calculate the distance between 2 points. So for example, let's say we have a point V and point U, and we want to calculate the distance between U and V. I don't actually like this picture. If you take this as a vector, yeah, by the parallelogram rule, yeah, so this is vector V, this is vector U, because you can look at points as points, or you can look at points as the vectors that point from the origin to that point. Okay, so and u minus v would be u minus v would be here. Yeah, it would be pointing in this direction, but we're interested in its length. So in order to calculate that, you just take in order to calculate the length of u minus v, you just take this u minus v, and for the first coordinates, for the second coordinates, for the third coordinates, you square them, and that's how you get the distance. Also, let me think. Yeah, also you could think about it in a still as a let's say we have these 2 points, right? So this is point U, this is point V. And if we look at those as a Pythagoras theorem, Pythagoras is basically everywhere. This guy left its mark on everything. U1, U2. Okay. It doesn't matter because we square this. This is V2, this is V1. So then we created this right triangle. It's not very right. Fortunately, not very straight. So this, yeah, this is what I need. And the length of its sides is V1 minus U1. And here we have V2 minus U2. Yeah, but I should have named this point U and this point V in order to correspond to this formula. But since we're squaring, it's the same thing. Yeah, so in order to calculate this length, the hypotenuse in this right triangle, you just need to add the squares of its sides and then take the square root of that. So V2 minus U2 squared plus V1 minus U1 squared, and then take square root of that, which is the same thing as here. Just if you swap their places, since you take the square, it would have the same value, and it would be positive. So this is u minus v, the distance between points u and v. Okay? Any questions? Clear? Okay, good. Good job. Huh? Yeah, I wanted an example. But okay, I think we don't need an example in this part. Maybe we can do one small example. Yeah, well, we have enough time to do a small example, so it's okay. Let's say we have a point of 1, 1, and a point of 2, let's say 2, 3. Yeah, so this point has coordinates of 1, 1. This point has coordinates of 2, 3. You just take the difference. So 2, 3 minus 1, 1. You have 1 and 2, and you square that. So this is square root of 5. That's this distance. Square root of 5. Okay? This should be fairly easy. Yeah, so we're done with inner products and lengths. The next topic is a bit long. Do you want, I don't think we need a break. We can take a break here because this topic is quite long. We can take a break here of 10 minutes. And this topic is also very small, but these two are large, so they would together take maybe an hour and 10 minutes or an hour and a half. So, but we have enough time to cover those. So we can go on. But if you guys want a break, you can just tell me. Let's do a break. It's so much theory. Okay, let's take a break. I also need caffeine. Let's take a 5-minute break. So we'll just take a break. It's okay, no worries. I also want a break. Okay, I think we can get back to stuff. I hope you managed to get your coffee. I also needed some caffeine, but I'm bougie, so I'm drinking matcha. I can't handle coffee. It's too much. Okay. We are back on track, right? I need some confirmation in the chat that everybody's present or somebody. Okay, let's go on. So orthogonality. Yep, so two vectors u and v in Rn are orthogonal if their dot product or inner product is 0. Okay, if you multiply them just as I showed you, so if u1 v1 plus u2 v2 plus dot 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 plus un vn equals 0, then that means that u and v are orthogonal. Okay, and vice versa. If they're orthogonal, their dot product is also should be 0. If you've seen the other definition of inner product, this should be just obvious. I don't know if I want to explain this another definition to you, but let's just go on and I'll see if I need to. So are we clear on this definition? I think we are. This is just that definition. If their dot product is 0, they're orthogonal. And then for a subspace V, define V orthogonal as the set of all vectors x such that x multiplied by v equals 0 for all v in for all w in w. V and v orthogonal are subspaces that are orthogonal to each other. Let me give you an example. Let's say we are in 2 by 2 space, 2D space. And let's say we have a space that is a span of vector 1, 0. So standard E1. And let's say a standard E2, 0, 1. Yeah. So this is a subspace by definition of R2. Yeah, because it contains 0. This whole line is a subspace of R2. It contains 0. If you multiply anything by E1, it's still on this line. If you add two vectors that are on this line, they're still on this line. And now I declare that the, let's say V is span E1, and V orthogonal is the span of E2. Yeah? Let's just check if E1 is orthogonal to E2. I think this is also 1. So we could also write it like this. So 0, 1 matrix multiplication, or not. Yeah, so row by column, we get 0. So they're orthogonal to each other. And if you take any two vectors from this span, so let's say vectors like 5, 0, and 0 minus 11, you would still get 0. So this is from V, this is from V orthogonal. And in 3D space, we could take a plane. Yeah, let's say we are taking a plane. This is X, this is Y. I'm not sure if I'm drawing the orientation correctly. So let's say our V is this plane. yeah, this plane. So any vector from here would be orthogonal to vectors that are in the span of E3, in the span of vectors of this sort, so 0, 0, z. So anything from here, yeah, so let's say multiplied by x, y, 0 as a dot product, yeah? So if you multiply these two things, they would give you 0. So in this case, V is span of 0, yeah? And V orthogonal is span of 0, 0, 1. Okay? Is this part clear? Good. I think we got the orthogonality and orthogonal spaces, subspaces. This thing. So let's just read this and try to comprehend this. The orthogonal complement of a row space of A is the null space of A. So row space is basically the same thing as column space of A transposed. Because if you take a matrix and if you just flip it on its side, transpose it, the rows would become columns. And we could talk about the transposed matrices column space, which would be the same thing as the row space of the initial matrix. So let's just go through this definition first. The orthogonal complement of the row space of A is the null space of A. And the orthogonal complement of the column space of A is the null space of A transposed. Yeah. So the orthogonal component of the row space of A is the null space of A. Yeah, so basically the same thing as here. And let me just write a few equations. The row space of A is the same thing as the column space of A transposed. And the column space of A is the same thing as the row space of A transposed. So, okay. So this could be just rewritten as column space of A transposed is orthogonal to the null space of A. And this is, yeah, this is something that you know. Is this part clear? Okay, good, good. Yeah, so let's do an example. Determine the orthogonal complement of the column space of A. So first, let's just remember the theorem that the orthogonal complement of the column space of A is the null space of the A transposed. So we just transpose A. As you can see, the first row became the first column. The second row became the same second column in the A transposed. And let's find its null space, which is immediately clear that the null space is just 0 vector. Why? Because basically every column is a pivot column. If you divide the second column by 2, it would become a pivot column. This is just linear combination of the first row. If you divide the second row by 2, you would see that the second column is also a pivot column, and the third row is just a linear combination of the first two. That's why the null space is 0. Why? Because we don't have free variables. in here. The null space is non-zero when there are free variables, which is immediately clear that the null space is equal to 0. Yeah. So the orthogonal complement of the column space of A is 0. Okay. Well, 0 vector is orthogonal to everything, because if you, by the definition, if you multiply anything by a 0 vector, you would just have 0. Yeah, I mean, as a dot product, in the sense of dot product. So if you multiply, let's say u by 0, you'd have u1 by 0 plus dot 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 un by 0. It would be 0. Yeah, so 0 is orthogonal to everything. Was this clear? Okay. You can ask questions whenever. It's okay to ask questions. And the set of vectors in Rn is called an orthogonal set if every vector is orthogonal to the others. Yeah, so let's just take this in. So if pairwise dot product of like any two vectors that are not the same, yeah, so let's say where I and j are not equal to each other, their dot product is 0. For example, you've just seen that these two vectors form an orthogonal set in R2, and in R3, can someone name me the third vector? It could be anyone, any vector. Yeah, exactly, 0, 0, 1. Well done. So this is in R3 orthogonal set. Yeah, orthogonal sets. They're not the only orthogonal set. It's just the simplest example I can give. I can think of. So, for example, let's just show that U1, U2, U3 is an orthogonal set, where U1 is this, U2 is this, and U3 is this. So let's see. First of all, you just pairwise multiply them. U1 by U2. Yes, so U1, if the first coordinate is 3 multiplied by -1, plus the second coordinate multiplied by, plus the third coordinate multiplied, you just calculate this, -3 plus 2 plus 1. This is obviously 0. The same goes for U1 and U3, for example. Let's see. 3 by -1 over 2. This is -3 over 2. 1 multiplied by -2. And then 1 multiplied by 7 over 2. So this is -3 over 2. This is -4 over 2. So together they are -7 over 2 plus 7 over 2. This is 0. And then let's multiply U2 by U3. U2 by U3. You just pairwise multiply them. And you also see that they are, in fact, orthogonal to each other. So -1 multiplied by -1 over 2. This is just 1 over 2. Yeah, so this is just 1 over 2. This is just -8 over 2, because this is together -4. You could just write this as this vector. So this is 7 over 2. So 1 over 2 plus 7 over 2 is 8 over 2, and then -8 over 2, this is 0. This is just arithmetic. Each pair of distinct vector is orthogonal. Each pair of distinct vectors is orthogonal. So U1, U2, U3 is an orthogonal set by definition. We just proved this. And you give an example where we do not have orthogonality. Yeah, I can. So let's say 1, 2, and 1, 1. As you can see, they're not linearly dependent on each other. They're not multiples of each other. Let's say this is U, this is V. Now let's calculate the dot product. I think I can give it to you guys. Just tell me the number. I'll open up the chat. What is the dot product of that? So it's not 0. It's 3. Yes, so it's 1 by 1 plus 2 by 1, which is 3. Yes, so U and V are not orthogonal. Are not orthogonal. Okay. Now, an orthogonal set of vectors is a linearly independent set, and hence is a basis for its span. Yeah? So there are no redundant vectors. They could not be expressed as a linear combination of each other, yada, yada, yada. The orthogonal set of vectors is linearly independent. And if we have in Rn an n set, n orthogonal to each other vectors, a set of n orthogonal vectors, this means that we have basically a basis for Rn. I think that was I was supposed to say. Yeah, orthogonal basis for a space W is a basis that is also an orthogonal set. That's what I wanted to say. Where, why, who, what, when, where, and why. Where's the yes. Was I planning to give me a sec? Yeah. This is the theorem. Let's see. Let's U1 UP be an orthogonal basis for a subspace V in Rn. And for each y in V, the weights in the linear combination are given by this equation. I think this is the time where I can introduce another definition of the dot product. Yeah, let's do this. So another definition of the dot product is this. Let's say we have two vectors in 2 by 2 space, but this is applicable to any space. Yeah, this is one vector, this is the second vector. Let's say this is U, this is V, and this is the standard basis X, Y, so E2, E1. Yes, this is angle alpha. This whole angle is beta, and the angle between them is theta. And also I can say that U1, U multiplied by, U multiplied by V, so inner product of U and V is by cosine theta. This is cosine. Okay. I think this is fairly clear because, well, it's not clear yet. Okay, let's just go over this in a bit of a detail. So this is V, right? We can express its coordinates through its length, right? And the alpha. Why? Because V1 would be equal to, so this thing, this is V1, would be equal to what? It's a side that is adjacent to alpha, meaning that it would be the length of V, yeah, so the hypotenuse multiplied by cosine alpha. And V2 is a side that is opposite to the angle alpha. So this is v1. This side is v2. Projection here, this is v2. And it's defined by this formula. Yeah, so this is just basic trigonometry. And the same thing we would have for, let's choose red, for u vector. Yeah, u1 equals, but with just different values. Cosine beta, yeah, and u2 equals e sine beta. And if we just remember the formula for the dot product that we just had, so uv equals u1 v1 plus u2 v2. If we substitute for these values in this formula, yeah, you would have, in here you would have u v cosine alpha cosine beta cosine alpha cosine beta. Let me just swap them. Cosine, it doesn't matter which side we multiply by which, because multiplication for numbers is commutative. I can just do this and this. Where's the, oh, shoot. Where am I? Yeah, so cosine alpha plus, we just do the substitution. Sine beta multiplied by sine alpha, which is equal to, we just take u and v out of the brackets. Yeah, and we have this thing, cosine beta cosine alpha plus sine beta sine alpha. And this is a trigonometric formula for cosine beta minus alpha. And if you look here, you would see that theta is beta minus alpha, which is just what I wrote. U v cosine theta. Yeah. So these two definitions of the dot product are equivalent, at least in 2D space. In 3D space, this is also true. You just need to do more trigonometry. So yeah, and this formula is basically a projection formula. If you look closely at this, let's say we have to, is this part clear? What I just explained? These two definitions of dot product. Yeah, good. Okay. So this is just the projection formula for basically you project y on uj. And let's say we are in 2x2 space. In 2x2 space, again, 2x2 is just easier to draw. And this is two vectors, u1, u2. And you have vector y. So if you project it here, yeah, like this, you have kind of a vector alpha, yeah? Let's say a vector theta, yeah? So let's say theta. So by this definition, what do you have? Y by uj is just length of y multiplied by the length of v. Yeah. give me a sec. Yeah, so the formula for projecting something, projection y. Give me a sec. I kind of need to give myself a bit more space here. The projection formula is in this form. So projection uj, u1. We are projecting y on u1. u1 y. It's in this u1 norm u1 by norm u1 by u1. So this is the projection. It's pointing in the same direction as u1, but it has a certain length, and this is its length. Yeah, so let's see. Y by u1, if we just write this out, this is basically the length of this side, but why do we need to divide by the square of the norm of u1? In order to get a normalized vector, because u1 is twice here, it's basically as projecting y onto a normalized vector, where e is u1 divided by the norm u1. Yeah, so because it's here twice, we need to divide it by twice. And if you just take a closer look at this formula, yeah, so let's say for this part, so this term is just yeah, so this term is just y by u1 divided by u1 multiplied by u1. So this is the dot product, this is the coefficient. Yeah, so this term and this sum is just the projection of y onto u1. Okay, is this part clear? Okay, good. If you have any questions, don't hesitate to ask. It's okay. I will go over this if need be. We have enough time. We have a bit less than 2 hours still. So let's do an example. Let's do an example. Let's say S is U1, U2, U3. Is the same set as in previous example where we had checked whether those three vectors are an orthogonal set. So they are orthogonal to each other. So now we're just basically trying to express vector y as a linear combinations of vectors u1, u2, u3 in S. So how do we do that? We calculate these terms and we multiply them by the corresponding u1, uj, yes, so here. And then we add them up, and this basically becomes a linear combination of our vectors from the set u1, u2, u3. Let me just show you. This is a part of the book. So you just multiply. Let me just remind you what u1 was. It was 1. What was it? Huh? Yeah. This is something new. Okay, let's just keep it. I don't think I can copy that. Yeah, so we basically calculate this. We multiply u1 by y by u1. We get this. We multiply. Yeah, that's correct. 1, 1, 3 or 3, 1, 1. Yeah, so I don't think I need to copy those. I should have written them out so I could easily put it. Maybe I did. Can you give me a sec? Yeah, this is what I need. And also here. Just so you can check this. So we multiply y by u1, which 6 by 3 is 18, plus 1 minus 8, which is 11. And if you calculate the length of u1, it is 9, plus 1 is 11. This is the square of the magnitude, actually. And then you do this. You multiply y by u2, the same calculation. And you calculate the square of the length of u2, which is 6, and then the square of the length of u3, which is 33 by 2. And that's how you write the linear combination of u1, u2, u3, which is equal to y. Yeah, so I think this is also quite clear. Can you write a line down? So yeah, so you want me to calculate this, right? I can do that. That's not a problem. Let me just clear some space. So let's calculate 6, 1 minus 8 by 3, 1, 1. It's okay. So row by column, yeah. 18 plus 1 minus 1. Maybe I need more detail here. 6 by 3 plus 1 by 1 plus minus 8 by 1. No. Yeah. And this is equal to, this is minus 8. So this is equal to 11. So this should be fairly easy, right? Nope. That's not what I need. I need this smaller. Yeah, so I would have. And then we just calculate u1 by u1. So u1 by u1 is 311 multiplied by 311, which is 3 by 3 plus 1 by 1 plus 1 by 1, which is 9 plus 1 plus 1, which is 10. This is what you wanted, right? Yeah. So 6, 1 minus 8 is just the definition of y. It's okay. Yeah, and that's how we get the first weight in this expansion. in this linear combination. You do the same thing for these two and for these two cases. And that's how you get the linear combination of vectors S that is equal to Y. So basically, you are expressing Y in the basis of S, because in R3, as we just said, U1, U2, U3 form a basis. Why? Because their number, we have 3 of those, and the dimension of R3 is 3. So they're linearly independent, therefore they span R3, and they are a basis. And you can do this for any vector, Y, in R3. You could write it as a combination of those two. That's why we do this. Is this clear? Why U1 by U2? I might have, where?
No, sorry, I read U1 times U2, but it's an equal sign, not a 2. So never mind. But I do have a question, because you said that U1 times U1 is 10, but then in the thing it says 11. Is that like
it's just me being.
Oh, okay. Sorry.
It's just me being. Thank you. I'm just being a bit stupid sometimes when I don't get enough sleep. Sorry. It's okay. Thank you. As you can see, I'm not a machine. Yeah. So this is that. Yeah. So orthogonal projection. Remember I wrote the projection formula. So we are projecting onto V, Y. Yeah, so V is our space, kind of, and Y is the projection. Yeah, in this case where I just yeah, so Y could be written as sum of two vectors, Y hat and Z. Yeah, so Y could be written as Y hat plus Z, where Z Y hat is just Y hat is a projection, and Z is Y minus Y hat. They just cancel out, and you get Y. Yeah, so that's very clear. For example, we have a subspace W, and we want to project our vector Y onto it, and you get Y hat as a projection. And Z would be then orthogonal to, Z is orthogonal to V. Yeah, to our subspace V, in this case, it's a plane. And here, yeah, so here, is the projection onto L. Yes, so U is in, that's remember I wrote this formula. So U is in V. Yeah, is just a vector in V, kind of. So Y hat is called the orthogonal projection of Y onto U, and Z is called the component of Y orthogonal to U. So basically, Y could be written as the sum of two components. One is in our space V, another one is orthogonal to space V, okay, to the subspace V. So I just explained you this projection formula a bit later, a bit previously. So let's do an example. So let's say we have Y and U. Find the orthogonal projection of Y onto U. Then write Y as the sum of two orthogonal vectors. One is in the span of U, and 1 is orthogonal to u. So remember, y would be equal to plus z, where z is y minus y hat. Yeah, so and z would be orthogonal. This is the orthogonality sign to u. And y hat would be some scalar, this particular scalar, cu. Yeah, cu. Let's see. So first you calculate the dot product. This is the exempt from the book, and they kind of write dot product like this, they do not transpose the first one. So this is just 7 by 4 plus 6 by 2, which is 28 plus 12, which is 40. And here we have 16 plus 4, which is 20. Yeah, this is the length of u squared. And then we just substitute those values in this formula, and that's how we get y hat. So 40 by 20u, so 2 times. This is the components of y hat. Yeah, so we just substitute it into this formula. We got our y hat. And then in order to get z, we need to subtract from y hat. Yeah, this is our z, the orthogonal component, which is minus 1 plus 2. And now you can check if you just add y hat plus z, you would get 8, 4 plus minus 1, 2. You would get 7 and 6, which is equal to y. So everything is correct. Are we clear on this part? Good. Where 2 comes from? You mean here? 40 divided by 20. Okay, so let's go on. Yeah. I just animated that. This is another example. Or not. Yeah, I just sum these two vectors. Here we're just checking that y hat and z are orthogonal to each other. Here we're just checking that y hat and z are orthogonal to each other. Remember, so this was our z. Yeah, so y minus y hat multiplied by y hat, which is 8 multiplied by minus 1, 4 multiplied by 2, minus 8 plus 8 is 0. So y hat is orthogonal to y minus y hat. So we are done with example 3. No, we are not. Okay, so yeah, this is the picture. This is the picture. So here we have a right angle. This is basically this vector. Yeah, so this vector is orthogonal. The same vector is here. Vectors are basically everywhere. They just need to, yeah. And y hat, as you can see, is in the span of u, because it's just u multiplied by some value. In this case, it was 2, I believe. Yeah. So this is the picture that illustrates this example. I think we are finally done with this one. Let's see. Who wants a 2-minute breather? So the projection is in the span of u. Yes. Yes, because y projection, let me get back to this. Let me go over the questions. So the y projection is in the span u, because y projection, yes, y hat is to u, yes, and y minus y projection is orthogonal to u too, yes, because if something is orthogonal to a vector from the span, it's also orthogonal to the vector that we are spanning, basically. We can check this. Where was u? U is 4, 2. So 4 and 2. So this is our u. We are checking whether u multiplied by y minus y hat is orthogonal to u. Yeah, so this is u, vector u. It's not 4, it's u. Multiplied by minus 1, 2. Yeah, as you can see, 4 multiplied by minus 1 plus 2 multiplied by 2, which is equal to minus 4 plus 4, which is equal to 0. So this is u. Yeah, as you can see, y minus y hat is orthogonal to u as well. And by the definition, the dot of orthogonality, if you have the dot product of two vectors equal to 0, this means that they're orthogonal. And remember the definition that I gave you, y minus v. Yeah, so you have their values v by cosine theta. So what does it mean that something is orthogonal to something in normal school geometry? That's the angle between those two lines, for example, is 90 degrees, right? And you guys probably know the cosine of 90 degrees is equal to, what is it equal to? The cosine of 90 degrees. Cosine of 90 degrees, or no, it's equal to 0. It's okay, guys. Math is hard. Math is hard. There's a lot to remember, but cosine of 90 degrees is 0. Okay. Yeah, so where was I? Yeah, so by this definition, we can also see, by this definition of dot product, cosine of 90 degrees is equal to 0. Therefore, this whole thing is also equal to 0 if two things are orthogonal. So, yeah, because theta, if two things are orthogonal, the angle between them is 90 degrees, meaning that cosine of that 90 degrees in this formula becomes 0, and the whole product, the product is also 0. Do you guys want a 2-minute breather just to clear up the head? Yeah, me too. I need to just take a second. Okay, I think we can continue, right? Is it okay if we continue? Okay. So just another definition. Orthonormal set is a set of an orthogonal set of unit vectors. So orthonormal set is an orthogonal set of unit vectors. So just an orthogonal set with extra property that every vector in the set has lengths of 1. So actually we can turn any orthogonal set into an orthonormal set just by scaling each vector by its length. Yeah, so let's say we have A1, A2, A3 as orthogonal set, or orthogonal set, and then A1, A2 divided by the norm of A2. I'm sorry for the writing. I'm trying, but yeah, I can't write more. It just takes. Actually, I can. I just press more. But then mine's. This is orthonormal set. Orthonormal set. Okay. So this should be fairly clear. Okay. Yeah, the curse of two left hands. Yes, that's true. I feel like a JoJo character. Show that the set of V1, V2, V3 is an orthogonal set and then produce the orthonormal set. Yeah, let's do this. Step 1, show that V1, V2, V3 is an orthogonal by showing that the inner products of all combinations of vectors is 0. So let's just multiply those two pairwise. So V1 by V2, V1 by V3, V2 by V3. Let's do that. As you can see, V1 multiplied by V2 is 0. So 1 by 1 plus 1 by minus 1 plus 0 by 3 is 0. Then V1 multiplied by V3 is also 0. And then V2 by V3 is also 0. So yeah. Then we just normalize them by dividing them with their own length. So V1 we are supposed to divide by square root of 2. And that's how we get W1, which is a unit vector because its length. Something is amiss here. It should be like that. Yes. No. It should be 1 over square root of 2, 1 over square root of 2, and 0. There's a typo here. I guess I didn't write fraction in the LaTeX when I wrote this. Yeah. So let's do the second one too. I think, yeah. So let's do V2 as well. So for V2, its length would be square root of 1 plus 1 plus 3 squared, 9, which is square root of 11. So then W2 would be 1 over square root of 11, 1 minus 1, 3. Yeah, I don't know how to fit this here. 1 over square root of 11. You get the idea, I guess. Let's just do a small training. Calculate me the length of V3. You can write square root as SQRT, and then brackets, and then the value that is under the square root. What is the length of V3? What should be under the square root? Okay, 24. Why 4? Maybe you were calculating something else. Okay, so 3 squared plus 3 squared. The signs. Yeah. So you just yeah. So 3 squared plus 3 squared is 9 plus 9 is 18, and plus 2 squared is 4. So 18 plus 4 is 22, and then B3 would be 1 over square root of 22, which is 3 minus 3 minus 2. Yes. 3 over square root of 22 minus 3 over square root of 22 minus 2 over square root of 22. So this is your V3. Okay. Let's go on. Let's see. Yeah, so orthogonal decomposition theorem. Let V be a subspace of Rn, then each y in Rn can be written uniquely in the form of y equals y hat plus z, where y is in the W and z is in its orthogonal component. In fact, U1 UP is any orthogonal basis of W, then y hat is expressed like this and z is expressed like this. So remember, we're basically just combined two ideas. Here is just, remember when you had an orthogonal basis in R, N, and you could write any vector as a linear combination of that orthogonal basis. And also we had a vector that could be expressed as, yeah, so this is, yeah, so we had vector y, this was y hat, orthogonal projection, and this is then this is just z, which is equal to y minus y hat, and this is v. So z is in v orthogonal and y hat is in v. Yeah, we are there's an orthogonal projection onto a basis v, similar to what we did when projecting onto another vector. Yeah, is this part clear? I think it is. Okay. Yeah, let's do an example. V is a span of those three vectors, and find the orthogonal projection of this vector, let's call it Y, onto W. First step, we need to calculate the weights in this expansion. This is C1, this is CP. What we do here? Well, we just basically multiply Y by V1. Let's call this V1, V1, V2, V3. Yeah, and this is a square of the length of V1. Then you just, this is the dot product. Yeah. And that's how you get the weight. So now we basically have Y hat, which is equal to 2 V1. And then we need to calculate the next step. Let me just, the next step would be to calculate C2, C3. Yeah, so let's assume we just did that. 5/11 V2 plus 0 V3. This is our Y hat. Yeah, like in this theorem. And let's go over to the next slide. Yeah, we just did that. Let's calculate it. We just substitute V1, V2, V3 by those values. And that's how we get our Y hat. This is a Y hat, Y hat. This is just a scalar by a vector. These three are vectors. I didn't make them bold. And then we calculate Z. Remember, it's equal to Y minus Y hat. And we just take the values of Y, we subtract the values of Y hat, and that's how we get Z. Yeah, that's fairly easy. You should know this. Well, yeah, you just know this probably. It's just arithmetic. And that's the solution for this. Yeah. And the distance of Y to W is the length of this vector. Yeah, so if we consider, so this is V, and this is vector Y, or point Y. And this is Z. Yeah, so Y hat, this is Y hat. So the distance between, yeah, this is also Z. The distance between Y and W, a subspace of R4, is the length of Z. Why? Because it's orthogonal to W, and its length is exactly that difference. Remember when we calculated the inner product and we wanted a distance between 2 points? Yeah, so we're basically calculating the distance between this point and this point, which is a vector of Z, and the distance is the length of Z. Is this part clear? Can you repeat what Z and Y project define? Y project define. Yeah, so Z is like a definition of it. So Z is, so we had an initial vector Y, and we projected it onto W. Yeah, Y minus projection on W, Y, where this is equal to Y minus Y hat. So Y hat is projection y hat is projection, basically like a shadow of y on w. For example, you could think about this. You have a pole that's kind of stuck into something, and it's lit right above. And the shadow on this plane would be this part, yes? So the projection is basically a shadow, if you imagine this. And so y hat is the projection onto v of y. So this thing, yeah? It's a projection. It's a shadow of y on v. And z is kind of the distance between the end point of y, and the length of z is the distance between end point of y and end point of y hat. And z is also orthogonal to y, to w, and it's also orthogonal to y hat because y hat is in the span of basis vectors of w, or just an element of w. Did that clear? Yeah, okay. Good. We're just a bit, yeah, we are finally done with orthogonality. I think symmetrical matrices is just 2 slides. It's very easy. Gram-Schmidt process builds up on what we just learned. Do you guys want a 1 or 2 minute breather, or do you want to go on? Break. Okay, let's just do 2 minutes. Let's not do too long, just 2 minutes. I am searching for videos that could help you understand how to solve polynomial equations. And most of them are okay, but yeah. So I think we can continue. We have just 2 topics for today that were previously planned. We might look at the LU decomposition and a few questions from one of the previous exams, if we have time to that. Let's just continue, okay? So Gram-Schmidt process. Yeah, it's a bit too early for that. We have 7 minutes. So I want you guys to go over to your, in a few minutes, I want you guys to go over to your email address and or to scan this QR code and to evaluate this course, because it's really necessary for Athena, but I will do this in 7 minutes, okay? Because I don't think you can evaluate it just yet, or you could try. So I'll just do this a bit later, okay? Oh my God. That's how math makes me feel. Oh my God. Yeah. So let's go on. I need some pluses in the group chat, please. Okay. So why do we even need Gram-Schmidt process? Let's say we have some basis. I don't know what, some basis. And we can, by using this process, we can orthogonalize it. I mean, we can transform this like random basis into an orthogonal one, meaning that each vector in this new basis is orthogonal to the other vectors, which is great because by then we can just express any vector in this R as a linear combinations of those new vectors in a very easy way. You have just seen that formula. Yeah. So let's do this. First of all, we are given a basis x1, xp in a non-zero subspace W of Rn. And we name x1 as the new first basis vector in our new orthogonal set of vectors. The second one, the second vector, we are taking, remember this was y, this is basically y hat, yeah? So this is y, this is y hat, and this is z. So by design, v2 would be orthogonal to v1. Now we basically created a plane, yeah? We basically created a plane, v1, v2, and in here, this is y hat, this is the new y hat, this is the new y, and this is the new z. So v3 is by design orthogonal to v2 and v1, and so on and so forth, because we might have infinitely many dimensions. This part is harder to understand because we don't have multidimensional eyes, we just have 3-dimensional eyes. So this is how we create, this is how we construct from a random basis an orthogonal one. Okay, is this part clear? Good. I can go over this again, but I think it's better to do this on an example. So let's say we are given the following vector. As you can see, this is actually a question from the exam, so it's relevant. In a linear subspace V, yeah, span of V1, V2, V3. Determine an orthogonal basis for V. Yeah, hint, use Gram-Schmidt algorithm. So the first thing that we need to do is we need to name the first vector as our first thing. Yeah, so we're going to construct an orthogonal basis y1, y2, y3. So we say that let y1 be equal to v1. Yeah, this is the first step. Then, by definition, then what we do, we use this formula. Yeah, we use this formula. Yeah, so y1 minus, well, yeah, y1 minus this thing. It's supposed to be v1, but that doesn't matter. And that's how we create our second vector. Let's just, it's supposed to be v1 actually, but that's okay. Let's just do the calculation. So v2 okay, this is a better formula. So v2 minus this, yeah, so this was y hat, this was y, this was z in the previous topic. So v2 minus dot product of v2 by y1, and then the square of the length y1, and then multiplied by y1, and that's how you get y2. One last step. We have already gotten the, let's assume we did all the calculations, and that's how we get y2, which is luckily the same thing as v2, because this part was 0. Yeah, so these two vectors actually turn out to be orthogonal to each other. Any questions on this part? Why something we just memorized? Is it too complicated to understand? Do you mean this Gram-Schmidt process? Well, this is what I just explained to you previously. So remember, this is based on what I just explained to you previously. If you understood this part, yeah, so let me just go over this again. So if you understood this part, you should also understand the Gram-Schmidt process. Because this thing is what we subtract from y in order to get z. Z is what we need, because z is the next orthogonal vector. Okay? Okay, so actually we are just at the mark. So I want you guys to take a 2-minute breather. First of all, to evaluate this course. This is very important for Athena. My colleagues basically constantly ask me to ask you to evaluate this course. Please do that. This is very important for me. This is very important for Athena. And also, while you have this 2-minute small break, just take a look at at the notes that you took in the slides where I explained the whole thing. Yeah, so remember we did this part. Yeah, so y equals y hat plus z. So y is the projection part, and z is the orthogonal component. And when we are constructing our basis, z, which is equal to y minus y hat, yeah, z is the new orthogonal component. So let's say we are given y and some other vector. Let me think. Yeah, let's say we're given okay. Did you guys evaluate this course? Just put pluses when you scan this QR code, and yeah. So can you just do this, please? I need a few more pluses in the group chat in order to know that you evaluated it. Please, this is very necessary. How do I explain this to you? Thank you, Elias. Maybe one more person, and then I will go on. Thank you. This part is very theory heavy. I'm sorry that you have to deal with this, but yeah. So when we are doing this part, basically, so remember, this is the first vector. Yeah, so this is our basis. We name the first vector as the beginning of our orthogonal basis. Then we are projecting the second vector, x2 here, onto v1. Yeah, so let me draw you a picture. So for example, we had two vectors, let's say x1 and x2. Now we have projected x1 onto x2, and this thing is projection x1 on x1 of x2, and then x2 minus x1 is this thing. And this thing is x2 minus x projection of x2 on x1. Projection of x2 on x1. I think I need to draw a better picture. I think I need to draw a better picture. Let's do this in 2D space. So this is a random basis on a 2x2 plane. So this is x1 that we named v1, the first vector of our orthogonal set. This is x2. We just projected it onto our new v1. Yeah. So this vector is, let me just projection onto v1 of x2. So then this vector, yeah, this vector, maybe I can denote it in a different color. This vector, v2, is equal to x2 minus projection v1, so minus this vector. So here it is. Yeah. Let's say this is the origin. And v1 is orthogonal to v2. v1 is orthogonal to v2 by design, by what I just explained. And in 3D, this would look like something like this. So for example, we already constructed two vectors. Yeah, so two basic vectors. Let me change back to black. So this is this step. Yeah, so this is what we do here. And for example, we already constructed an orthogonal basis. Yeah, so just let's imagine that we do. And we have x3. Yeah. And let's project it onto this plane. Let's project it onto this plane. Somehow. No, I don't like this. So this is the plane. And let's project it. This is also an orthogonal projection. This is x3. And this thing, let me draw it in a different color. This thing, which is here, would be our new v3, which is equal to x3 minus projection onto this, let's call this v, onto v, x3. V is, no, let's not call it v, let's call it just v. V is span v1, v2. Yeah, so this is v3. This is how we create the second vector. Unfortunately, I'm not a good enough artist to draw in 4 dimensions. Yes, it's making sure that each v is orthogonal to the next. Yes, by design, by the construction of this process, each new v would be orthogonal to the previous vectors by design, because it's basically each new vector that we construct is orthogonal to the span, to the space that is formed by spanning the previous vectors. Okay, is this part clear? Because this part is the most important in the Gram-Schmidt process. Yeah, sehr good. Okay. Okay, where was I? So we had those vectors. We want to construct new vectors out of them. And we created the first v1. Now we are trying to find v2. Yeah, what I did just was correct. What did I tell myself? Yeah, this is okay. Now, let me just erase this. This is not needed. So new basis vector is new orthogonal basis vector. So by design, y1 is orthogonal by y2. Is this? Let's do the calculation. This is the projection part. Yeah. And it turns out that they were orthogonal to each other all along. We just got that. Now we completed the second step. We can do the third step. The last step, we need to convert v3 to y3 by, this is the projection onto v of v3. V is span of y1, y2. Yeah, this part is projection, just with a plus. Yeah, so v3 minus this projection gives us something that is orthogonal to that span, to the v. So v3 is orthogonal to v. And let's do the calculations. I believe I did them. Let's do the, let's assume we did that. And we have our answer. This is the new basis set that is orthogonal. We can check the orthogonality. Let me see if I did the calculations. Yeah. Was this part clear? Good. You can check your answer by checking if this orthogonal, if this is orthogonal set. Yeah, calculate all inner products and see if they are zero. So if y1 should be 0, y2, y3 should also be 0, and y1, y3 is also should be 0. Yes. That's how you can check this. Just by looking at it, you can see that minus 2 by 2 plus 4 by 1 gives you 0. So at least y1 by y2, y1 by y2 is 0. If needed, you can make an orthonormal basis by normalizing the vectors in your answer. What does it mean that we normalize something? Let me check if somebody remembers this. Don't be afraid to give a wrong answer, because if you do, make unit vectors. Good. And how do we make unit vectors? How do we make unit vectors? Divide them up. Great. Perfect. Perfect. Good job. Divide by the magnitude. And how do we calculate the magnitude? Let's just dig deeper. We can afford that because we're basically done. How do we calculate the magnitude of a vector? Yes, perfect. Great. That's the correct answer. Yeah, so we're done with Gram-Schmidt process. We can do a small break, or we can just finish with symmetric matrices and do a big break. And then we can go over LU decomposition and maybe go over your questions and some exam questions, okay? Okay, 2-minute coffee break. That's fine. That's fine. That's perfectly fine. I also might need a small coffee break. So if you guys want, we can continue. because we're basically done. Yeah, great. So one last topic, at least in these slides, is symmetric matrices. Let's say we are given n by n matrix A. So we say that it's symmetric if it's equal to its transpose. So for example, is this a symmetric matrix? Yes or no? Is it equal to A transpose? Yes, it's true. But what about this one? So B transpose is 1, 2, 2, 3. Yeah, we just turn this row into this column, and and this row in this column, and we can see that they're symmetrical. So basically, how to recognize symmetric matrices is to see that stuff on the diagonal doesn't matter, because if you transpose something, it still stays on the diagonal. But the stuff above the diagonal and below the diagonals should be sort of symmetric. So symmetric matrices are basically something like this thing. Yeah, so let's call S symmetric. Yeah, so the diagonal is stuff that is the same. Diagonal stuff doesn't matter. It could be anything. But the stuff here and stuff here should be basically equal. Yeah, just okay. And one more thing, symmetric matrices have orthogonal bases of eigenvectors. So that's what you need to know. And eigenvalues of those matrices, eigenvalues of symmetric matrices are real. Symmetric matrices are real numbers. Real as opposed to complex numbers. Do you guys remember what is a complex number? So complex number is a number of that sort, where I is a square root of -1. This is complex. And A, B are from R. But these eigenvalues are from R. That's what you need to know about symmetric matrices. And would you look at that? We are done. We are done. So questions? Let's do questions. Can you give an example of a non-symmetric? Yes, no problem. No problem. Let's do 2 by 2. So let's do C. So 1, 3. 1, 3, 2, 4. And C transpose. Let's do. So this row should become the first column. And this column should become the first row. And this column should become the second row. 2, 3. As you can see, C is not equal to C transpose. Yeah, they're not equal. Okay, but here we have that. This is true. And also B equals to B transpose. Maybe I could give you a larger example of a symmetric matrix. So for example, let me think of something. 1, 2, 3, 4, 5, 6, 4, 5, 6. Yeah, so this is also A. And let's calculate A transpose. So this row should become a column. So 4, 5. Yeah, so this row. Let's just do one thing. So dash. Yeah. So let me change colors. It's just a bit of rest. Okay. Let's say so first row becomes the first column. Yeah, so picking that. So then let me do the second row. 4, 2, 6, and 5, 6, 3. Let me do this. Now I used red for that, and I used a very non-recognizable color, purple here. Maybe I should use this neon green. No, it's not really visible, but yeah. So as you guys can see, those two matrices are the same thing. Yeah, that's true. Yeah, so their diagonals should be equal. And if you look at the reflection over the diagonal, yeah, basically if you kind of fold the matrix over its diagonal, as you fold, but reduce. Sorry, I forgot, but can I reduce the matrix to a triangle to get the determinant from the diagonal or not? Yes, you actually can, in order to get the determinant, but you need to remember two rules. If you swap two rows, you can do the row operations, but if you swap two rows, you are supposed to change the sign of the determinant. And if you multiply a row by a constant, you also should multiply that row, you also should multiply the determinant by that constant, okay? But adding to a row a multiple of different row doesn't change the determinant, okay? So I think that was that. We've just seen the symmetrical matrices, what they are. I think it illustrates it's good enough. Thank you, Peyton, for the explanation. You also did a good job. So basically, we have covered everything. This is just a bit of trivia about symmetric matrices. And if you guys have any questions on those topics, we can go over them. Any of those topics, in fact, just. You don't need to say sorry if you're asking something. If we have to go practice exams together. Yeah, we can. Just what I can do is I can show you what practice exam I have. Let me just save my notes here so they wouldn't save with notes. So I save this, export as PDF with notes, save. Okay, so it saves it. Now I will just stop the share. I think we should go over the LU thing. Yeah, we can go over the LU thing. Let's go over the LU thing. And then after, I think we will have time because LU is a small topic. I think I have this. Just let me do the thing. If somebody watched the Avatar Legend of Korra, you know, Julie, do the thing. I love the cartoon. One. Let me just do the thing. Open. Bases. Yeah. So this is. Wait a second. So let me just show you what I'm opening. Thank you. I'm trying. Julie, do the thing. Because I worked with kids. I mean, I am a professional tutor, in fact, and basically, if you're not fun with kids, they're just getting bored pretty quickly. And also, I am a bit like a kid. So this is the exempt from the book. Someone sent me this book, and I think you just did that. So why do we need LU factorization? It's usually motivated by the idea that, for example, we have one matrix and we have a bunch of linear equations connected to this matrix. Yeah, so basically we need to go do a lot of those linear equations solutions. And in order to do that, we can transform our A as LU. So lower triangle matrix, upper triangle matrix. And if we can do that to A without row interchanges, meaning we don't swap two rows, swap two positions, we can actually simplify our task. So if A is invertible, we could just compute A inverse multiplied by B1, but yeah, so this is basically motivated by a computational thing because multiplication is n times more complex than adding two things, and row reduction is mostly multiplication. So let's assume that we can row reduce A into an echelon form, meaning we have some kind of a step thing, yeah, in our A. So here's zeros without swapping to rows. So swapping to rows is prohibited. We cannot swap to rows. Let me see the chat. So okay. The teacher also just published his solutions to the practice exams that didn't have them before. Okay, if you guys have that, you can send them to me via WhatsApp group, if you have those, and we will go over them together. If you want, just send it to the WhatsApp group. Okay. So now let's assume we can decompose by row reduction. It's for the exercises. Okay, if you guys have something, just send it to me. We will finish with this, but yeah. Let's assume we can without row reducing. This means that, let's say U is basically A that is converted into an echelon form with row reduction operation, except row exchanges. Then we basically can construct another another matrix L, basically kind of encodes all those row operations. And it would be an upper triangle matrix and lower triangle matrix, meaning that the upper part would be zeros and the lower part would be ones. And we can do that by computing, and we can solve this by computing two equations. So let's say AX equals B, and now A is LU X equals B. Now we say that UX equals Y, then this thing converts into Ly equals B. So basically we solve this first, and then we solve this thing, and that's how we get our X. Yeah, so we do two things. We decompose A into LU, and then we just simultaneously solve these two systems. Yeah, so first we can go from X to B by applying A, or we can go from X to B by applying first U and then L. Yeah, so here you can see that in this, yeah, you multiplied X by U and then by L. So is this part clear, guys? Okay. So now let's see what we can do. Here's an example. Let's see. Yeah, so we have a normal matrix. Let's assume that we can decompose it, and we are given the its factorization. So this is L, this is U. Why it's U? It's upper triangular. So we have triangle above, kind of this line that is not zero, and here we have this thing, a lower triangle matrix. Yeah, so it's kind of below the diagonal, but also includes the diagonal. And so first we're trying to solve L and B, and you can kind of yeah, solution LYB needs only 6 multiplications and 6 additions, because arithmetic takes place only in the column 5. Yeah, so this is B, like that. And yeah, and we get the solution, and then backwards we do the row reduction, and we get this part. Yeah, we do this solution. So remember what we did. We had AX equals B, then A decomposed into LU, and we had LUX equals B, and then UX equals Y, and LY equals B. First, we solve this thing, solved. And then we solve this thing. Yeah. So we kind of got this L from solving this matrix by Gauss-Jordan elimination. We got our vector y, and then we just plugged in this vector y in here in the system and did another Gauss-Jordan elimination and got our vector x. Finding x reduces to 28. This is just about computational stuff. So this is how we basically, this is the motivation why we do this, because it basically saves us time, computational time. Since you guys are CS, computer science students, you you kind of understand why saving computational time is important. Basically makes stuff work faster and require less energy. So yeah, this is the motivation why we do this. And maybe this is the most important part. Suppose A can be reduced to an echelon form using only row replacements that add a multiple of one row to another row below it. Yes, so basically we just kind of, in this case, there exists units of, well, this is basically a theoretical explanation why LU factorization is true. I think you guys can self-study this. I didn't have time to think it as much through. But yeah, I want just to show you how to do an example. Yeah, so I am getting to this. I'm getting to how we do the LU. Reduce A to an initial form of U by a sequence of row replacement operations, if possible. Place entries in L such that the same sequence of row operations reduce L to I. This is a bit unclear, but let's look at it here. So for example, this is our A. Since A has 4 rows, L should also be 4 by 4. So let's see. We are kind of the first column of L is the first column of A divided by the top entry. As you can see, the top entry is 2. So we divided the first column of A by 2, and that's how we got our first column in L. So remember, A is LU. U, we get U by doing only which operation? We subtract from each next row, the previous row, multiplied by something. Yeah, so we are getting rid of these values. We are decomposing A to U. Yeah. So as you can see, A became this thing. So we got rid of these values. So we got zeros here. And first column divided by 2, we just entered these values into our L. And on the diagonal, we just put 1. Okay? We just put 1 on the diagonals of L. Now, next step. We are dealing now with this column. Let me just show you. Now we're dealing with this column. No, not this column, this column. And we are killing these 2 values with this 3. Killing. Okay, so now in L, what should go in L? These 2 values divided by 3 by the same logic. Yeah, so these 2 values divided by 3. See? Yeah, so we simultaneously kind of decomposing A into U and also building the L. So that's now we got zeros here and coincidentally here, I think. Where's the Yeah, I understand. This should be that. Yes, that's now correct because this is B. If there are multiple B's, we can just stack them here and perform the same operations, and they would happen simultaneously. That's a very smart algorithm, actually. So yeah, so this is the contents of the second column. After we got to this stage, okay, so we're reducing to make U, and then adding what we removed to L. Kinda, not, we are row reducing A to U, but we are adding to L kind of the parts of the column divided by the first entry. So, for example, the first column, this is L. The first column of L becomes the first column of U divided by the first entry divided by 2. Then we kind of forget about, we're here, we forget about this part. We forget about this part, and now we are dealing with this submatrix. And we need to put in the in this part, yeah, so here are zeros, 0, 1, 0 here. We need to, this is the part of the column of the submatrix. We need to divide this by 3 and by the first entry. This is the first entry. This is from A. Yeah, so we had something here, it doesn't matter what. Yeah, so we divide this column by 3, we get the second column of L. Here are zeros. And then we do the same thing with this column. Yeah, so with this column. And it's actually 2, 4. That's the last column here, 2, 4. And that's how we get 2, 4 divided by the first entry, 1, 2. Nice. So this is L. And you can calculate that L multiplied by U is A. So that's the thing. Actually, I have, I don't think you need this part. I don't think you need this part because this is just something. This is just practice problem. And also I will send you a video, which in my opinion, explains this very well. In my opinion, LU decomposition very well. And now we can do practice exams. Are we clear on LU factorization? Okay, so let me just save this. Save these notes. Export as PDF. Let me just check if this thing exported. Great. I can send you my notes. If you guys give me a sec to send you the notes that I have. Let me just check if everything is in order. You need to do the thing. Slides. Change this. Oh God, there's so much stuff here. Yeah, I think this part, the slides are okay. The files is not corrupted, so I can send you those. Yep, this should be okay too. So let me just I think I'm done with that. Let me just, oh, exam 1 solutions, exam 3 solutions. Okay, this looks nice. Thank you, guys. Let me just see what I have here. Do you guys have the exams on your own? Okay. I'll just say with notes. I will go over. Yeah. I can't share the notes with the stuff with the notes because the file is too large. Okay, I will load it into the Google Drive and I will send you the slides with the notes afterwards, after the lesson. Let me just close this and close this. We have 10 more minutes and let's go over the exam questions together if we can. Change of faces, junk, algebra, testing exams. I think I can have a few more minutes to kind of go over with this stuff with you. So where's this thing? Same solutions. Where is it? Where is it? I see. Open with chicken. I see. So there was a disclaimer. So I don't know if we can trust this, but okay. Let me just adjust everything to the way that we could see this. So okay, share screen. Desktop, share. Gotta go to. Okay, thank you very much. Okay, so those who logged off, good luck. Those who stayed, we can go over stuff. We have 10 more minutes. So for which values do you guys see my setup, my screen? Yes, okay. It's not particularly nicely set up, but yeah. So the first question, for which values okay is the following matrix invertible? Basically, what you need to do here is to just check the determinants. Remember how I taught you, use the pattern. So go this way, go that way. Maybe I can just use annotation. So go this way, and then this triangle, and another color. And then that, this is with minus this and that. You check the determinant. And if the determinant, if there's such values of k that the determinant is 0, meaning that for those values of k, the matrix is not invertible. Clear all drawings. Okay. So then we have the same basically system corresponding to this matrix. Yeah, if you look at it closely, it looks well, 1, 1, x and z are, yeah, so these are basically the same equations. As you can see, the guy solved this the same way that I just explained. So in point B, yeah, so for values k, yeah, so he found the values of k should not be equal to -2 or minus and +2. Maybe I can make this a bit bigger. No, not 100%, 7%. Yeah. So here he found the clear. So here he found the values for k. And now for values that are not equal to 1/2 as 2 -2 and 2, the system has a unique solution. And for k equal to 2, we have we decompose. We use Gauss-Jordan elimination process, as he did here. And we have infinitely many solutions. And for k -2, we have a case of we have a case of 0, 0, 0, b that is non-zero. As you can see here, here it is. So this is b. Yes, so 12 basically this is equal to 0 equals to 12, which is impossible, meaning that for k equals -2, we have a case of no solutions at all. So for k equals to 2, we have infinitely many solutions, and for every other k that is not 2 or not -2, so r except these two values, we have just one unique solution. Let me clear up the drawings and ask a question whether this is clear. I think it is. Let's go over to, so for k equals to 1, find an inverse. Well, it's easy. You just stick A and the identity matrix, you substitute k for 1, and you just do the Gauss-Jordan elimination process until you get the inverse, and use it to find x, y, and z. And you use this formula to find x, y, and z is ax equals b. Then if you just multiply by inverse from the left, you get, and you use this formula to find x. So this should be fairly clear as well. Now let's see what D asks us. Let A denote the above matrix for k equals to 1. Use Cramer's rule. So to find y in B. So Cramer's rule was what? You in A, to find x xi, the ith component, you substitute in A b in the ith place, and then you calculate the determinant of ai and divide that by the determinant of a, and that's how you find, this is exactly what he did here, and that's how you find your xi component, and you do that for all xi. You do this 3 times and you find all the components. Yeah, so okay. So is this part clear as well? Many thanks for today. Okay, so you're logging off. Okay, good luck. Goodbye. So let me clear my notes. Let's see what comes next. So exercise B, exercise 2. So reduce this to a reduced row echelon form. That should be fairly easy. You know how to do this. Find the basis for the null space. Null space, what does that mean? So we need to find solutions for ax equals 0. So if A reduces to a matrix without free variables, we have a null space that is 0. But in this case, we have less rows than columns, meaning that at least one column should be corresponding to a free variable, meaning that our null space should not be 0. And let's look at what he did here. Let me just check where things are going. Maybe he solved it. Yes. So here I reduced this thing. Yes. So the last column is in a weird place. Yeah, so to find the basis for the null space, we must solve the ax equals 0. We did that in A. Yeah, so we basically did that, and we have one free variable, which is x4. We express the whole thing in x4. And so this vector that is multiplied by x4 and something else is the basis for null space. So our null space is basically one line in R4. And what was the question about the third part? Find the basis for row space and extend that basis to R4. So row space is the column space. We did that today. So row space of A is the column space of A transposed. Maybe he did this in a different way. So let me just see. To obtain the basis for column space of A, we take the pivot columns of A, thus ZR. Well, here he did the column space, but there they ask for row space. Well, if we flip this thing, on its, like, kind of take the A transposed, we would get 3, 2, 4, 4, 1, 2, 3, 4, 2, 4, 0, 0. Yes. And the column space would be the linear combinations of these 3 vectors. And just take any vector that is not in this column space, and you would get the basis for R4. So let's just think about it. I think I can take 0, 1, 0, 0, or something like that. And this would be the basis for. I just don't like, the only thing that I don't like here in his solution is that he talks about the column space of A. But there they ask for row spaces. I don't know. But I don't think this is the correct idea. yeah, this is not what they're asking for. Let me check the chat. Maybe you guys have ideas. I think what we need to do for this one is we need to, just as I said, we need to A transpose. So 3, 3, 2, 4, 4, 1, 2, 3, 4, 2, 4, 0, 0. Those columns are linearly independent. And we just add something else, like any vector. And we can check whether it's in linear combination of those two. I don't think it will be. Maybe even 1, 1, 1. And yeah. Let's just skip this one because his solution kind of confuses me. I don't think he is correct, but I'm not sure. And then let's go on to the third question, which is something that I solved today after midnight. I mean, sometimes my brain does stuff like that. It just refuses to go to bed if I have a question in mind. So let's just look at this first. Let A be a fixed 2 by 2 matrix. Let M 2 by 2 denote the vector space of all 2 by 2 matrices. So we remember what a vector space is. It's basically a linear space. Let H be the set of all 2 by 2 matrices such that AB equals BA. Show that H is a vector space of M 2 by 2. Okay, so let's see. What did he do there? Huh, this looks familiar. Yes, so A 2 by 2, M 2 by 2 vector space, H blah, blah, blah. Yeah, so basically 0 is obviously going to be in this because 0 by A is equal to A by 0. I mean, this is matrix 0, not 0 as a scalar, a matrix 0. So yes, so 0 is obviously in H. If we want to, if we take B and C from H, B plus C is also in H. And this is obvious if you just take B plus C to the A. This just also should be equal to B plus C. Let's just expand this. BA plus CA. And also AB plus AC. If this thing is equal to this thing by the definition of H, and this thing is equal to this thing by also definition of H, obviously both of those things are in H. Yeah, that's what he did. And 3 multiplication by scalar, this is fairly straightforward. This is the conclusive proof. Yeah, that's what I was thinking. Clear my drawings, clear all drawings. Now, let's see what's the next thing that we are on task to do. For A above, let K, let me just check the chat. I kind of forgot about that part. Any questions? What is the, what's the time constraints? I can spend like a few minutes with you to solve these 3. It's okay. So let's do B and C and D, and then I'll let you go. I mean, you can go whenever. I'll just be here to solve B, C, and D. I can spend like 20 minutes with you to explain this. It's okay. So let's see. Point B of the third question is let H be the set of all 2 by 2 matrices. No, I just read that. For A as above, let K be the set of 2 by 2 matrices such that AB is not equal to BA. Is K a vector subspace in M? No, because it doesn't contain 0. Why? Because just as I wrote, 0 by A should be equal to A by 0, but if 0 is in K, then we should have this. But this is not true, so this doesn't contain 0, therefore K is not subspace. This is an example of a not subspace. Yeah, for example, let's see what he did. What did he do? Too many stuff on the screen. Too much stuff. Too many stuffs. No, 0 is not in K. Yeah, that's true. So now let's look at point C. Find 2 matrices A and B that belong to H for any choice of A. Yep. I think I would have taken, he takes identity and twice the identity. You can also take the identity and 0 matrix. There is at least one non-zero element in H. Yes, there's at least one non-zero element in H. Therefore, the dimension is more than 0, more than 0. The dimension of H is 0 if H is just a 0 matrix. So we turned out the dimension of H is more than 0. There's more than one. There's at least one non-zero element. And now, as we solve ABC, let's do D. Let A be this. Describe all matrices as such that AB equals BA. This is pretty straightforward. You just do AB equal BA, do that to multiplication, and you look at what results. What is the resulting thing? Yep, let's see what happens here. This is something else. Okay. Let's see. So AB multiplied by this thing, yeah, we get this. And yeah, AB multiplied by this thing. This is fairly straightforward. So yeah, E1, 1, and 2. So what we end up with is, I think, a symmetric matrix. Almost. A symmetric matrix. Yeah, we end up with a symmetric matrix where it's in this form. So we do this multiplication, and we know that those coordinates should be equal. So this should be equal to this should be equal to this should be equal to this, and this should be equal to this. So we end up with a symmetric matrix of that sort. Yeah. Clear. And what's we kind of decompose the thing into B. We kind of decompose B into as a linear combination of those 2 matrices, and therefore the dimension of H is 2 for A. Yeah, for this specific A. Okay, so this is also fairly straightforward. Let's look at the 4th one. I don't know if I have it. Let me see. Yeah, there's 4. So let's see. If AB are square matrices such that AB equals 0, then BA is also 0. I've learned that that's not true because I've came up with example. I think you also came up with an example. Well, my example is also okay. Let me just show you what I came up with. So for example, I had two matrices of this sort. So 0, 0, minus 1, 0, 0, 1, 1. Yeah. If let's say this is no. No. Clear all drawings.